space station about 90 minutes to go once around the Earth. We know the mass of the Earth, and we are trying to figure out, well, how fast is the space station going if it goes around once every 90 minutes? And we know that 90 minutes is 5,400 seconds, which is what we're going to use for this problem, because we never use minutes, we always use seconds. So we have to convert that. So the first thing you might be looking to do is, okay, what's my velocity equation that I can use for things that are orbiting? And you look and you'll see that you don't have enough information to solve because you need the orbital radius to use the orbital velocity equation. So you say, oh, I can't do it yet. And you look around, you look around, you look around and say, I can't solve for velocity in one step. And in this problem, you can't. Sometimes that happens. So we're going to need to do first, before we can solve for velocity, because every equation we have with velocity in it has the r, or the orbital radius. So we're going to solve for the radius first. So that's what we're going to do. So we're going to go and take a look and say, okay, what is the centripetal force acting on the space station? Well, that's the force of gravity. So I know that the force of gravity equals my centripetal force. There. And the equation for force of gravity is big G, mass of the Earth, times the mass of the satellite, all divided by that orbital radius squared. And for centripetal force, I'm going to use the larger equation, which is the m 4 pi squared r over t squared version. So the m is the mass of the satellite, because that's going around, 4 pi squared r all over t squared. Now I can eliminate the mass of the satellite, because that's just going to cancel. And now I'm going to get rid of my fractions. Nobody likes to deal with fractions. So I'm going to multiply the r squared up over to the right, and multiply the t squared up over to the left, giving me on the left big G, mass of the Earth, times t squared equals 4 pi squared, and r squared and regular r becomes r cubed. Now what I'm going to do is I'm going to divide the 4 pi squared over to the left, so that's going to be the denominator, and then I do the cube root to get rid of the r cubed. So on the left side, I'm now going to have big G, mass of the Earth, t squared, all over 4 pi squared. And that would give us r, actually would give us r cubed, but we're going to do the cube root. And now we just have to plug in our numbers and solve. A lot of big numbers here, so hopefully we can fit them all in. So the G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. The mass of the Earth is given at 5.97 times 10 to the 24th kilograms. Our time is 5,400 seconds, and we square that. That's all divided by 4 pi squared. And now we have to do our cube root of all of that stuff to get r. And when we plug all that into our calculator, we get that the radius should be 6.65 times 10 to the 6th meters. So there's our r. Now we can solve for velocity pretty easy. Our very first equation we ever learned in uniform circular motion was that velocity is 2 pi r over t. We now have r, we had t right at the beginning, so we can plug in and solve. So velocity is 2 pi times 6.65 times 10 to the 6th meters all over 5,400 seconds. And when I plug that into my calculator, I find that the International Space Station is going about 7,738 meters per second.